Welcome to the second lecture on this topic. So now we will discuss the temperature model. In the first lecture, we discussed the power consumption model. So the temperature model is kind of physics heavy, not a lot, but there is some. So let's look at a diagram of a silicon package. So we have the small little chip over here. The chip is not very large. So the chip, even a big one, is roughly 400 or 500 square, which is nothing but 2 centimeters by 2 centimeters, right? So that's all that is there. So it's not very big. On the bottom of the chip, it's connected to the PCB, right? And that's the bottom means bottom in the slide, not the bottom of the chip. But the point is that here it is connected to the PCB with a ball grid array for connections. And the PCB is basically the motherboard which connects, which has other chips in the chipset. So because temperature hotspots form, there is a need to kind of spread the heat, right? So what you want is that you don't want any hotspots. You want to kind of spread and dissipate the heat. So you have a heat spreader, which is somewhat larger. So the spreader would maybe be like 6 centimeter cross 6 centimeter or 5 cross 5. So it is somewhat larger. It's like the size of half a thumb or maybe the size of a full thumb, right? Right. It's a thumb cross thumb pretty much, right? So a spreader would be much larger. It would be something like this. So its job, as I said, is to dissipate the heat and homogenize it, and finally have a heat sink which is even larger. So if I would say it's like this. So the heat sink, as you can see, has a bunch of fins, and you typically have a fan at the top. So typically on top of this you have a fan whose job is to kind of have air circulation such that air can take the heat away. But even otherwise, the job of the heat sink for having so many fins is to kind of increase the surface area, because the higher is the surface area, the more heat air can extract, right? So you want to keep the chip as cold as possible. So most of the heat actually flows vertically. The lateral heat conduction is not much. I wouldn't say it is not substantial. There is some, and that is often it creates a lot of issues. But most of the heat, by and large, flows vertically. The heat spreader is a nickel copper alloy with a thermal conductivity 369 watts per Kelvin, pretty much. And the heat sink, of course, has a much larger surface area which is artificially enhanced with these fins. And the lateral heat conduction and flow through the PCB is not more than 20 to 30%, because there is some heat flow like this as well. And also there is some flow laterally, and again laterally, so nothing goes via the sides. So we assume the sides are adiabatic. Adiabatic means that there is no heat flow, there is no heat flow through that interface. So again it flows through the sides, and then it either goes up, most of it goes up, some of it comes down. So this is a typical diagram of a silicon chip package. So just a small correction, the heat spreader's conductivity, as I said, is 369 watts per meter Kelvin, not watts per Kelvin. So I realized that's one mistake that I did. So this is also what we have measured in our lab, right? After kind of disassembling a processor. So it could be, plus or minus 10% of this. But broadly speaking, the job is to have a very good heat conductor here. It's a nickel copper alloy, and then furthermore pass as much heat as you can to the heat sink on top. So the heat sink has a fan above it, and the job of the fan is to remove the heat, and here you can clearly see the fins, right? The fins are clearly visible. The motherboard, so the motherboard, as you can see over here, we have, of course, these are our memory chips. Then we have the processor here, the heat sink on top of it, and the fan, right? And it looks like it has some other, liquid cooling technique. But the motherboard has all of this, right? So the motherboard has many of these huge heat sinks. One heat sink is clearly visible over here. So as you can see, the heat sink is here. There are many of these fins, and these fins effectively increase the surface area. And because they increase the surface area, what happens is that a lot of the heat is removed, right, via the heat sink mechanism. Of course, you need a fan, so you need some sort of an active mechanism to blow air on top of it such that it can remove heat. There are three heat transfer mechanisms. This is again basic stuff, but it's important to take a look at it. Conduction is where you need contact. So for example, all the heat that is passed around within the chip is all conduction because you need contact. Convection on the other hand happens because of fluid flow. So what happens is that you heat, let's say, the ground, you have a heater, hot air rises, then cold air comes and takes its place, it becomes hot, it rises. So there are these cycles form, right? So this is convective heat transfer. Convective heat transfer requires a fluid. So a fluid can be air, it could be water, anything, but it requires a fluid to take the heat and move along with it. Then you have radiation. Chips do emit a little bit of radiation, but not much. So this is dissipated as electromagnetic waves, mostly infrared waves. And radiative heat transfer we study a lot when it comes to black bodies like stars and planets and so on. But that is again not a concern here. So convection and radiation are not a concern here, but you may argue that removing heat from the heat sink involves convection. Of course it does. So that is where it plays a role, but not otherwise. Some little bit of basic physics, I know you don't like that, but a little bit. So let us say that we have this small little cuboid over here where the area of a face is essentially A, right, area units. Let it be SI units, meter square, so on. It doesn't matter, assume they are SI units. And let the thickness of this be delta x, right? It is on the x axis, delta x. And the temperature on one side is T1, other side is T2, and T1 is greater than T2. So this is one assumption we will make, right? And the other setup that we'll have is we will now extend this to another cuboid and kind of differentiate this. So we will say that, look, let heat entering on one side be Qx, the heat leaving on the other side be Qx plus dx, and the thickness be dx. So instead of delta x, which is like discrete, we made it continuous. So continuous will help us solve differential equations. So we made it dx, and it's simple, right? It's a simple cuboidal geometry. Heat entering on one side, the x-axis is qx, leaving on the x-axis qx plus dx, and we assume that on any of the other faces, no heat comes in or goes out. So this is the 3D view so this is what we will assume for the time being. So the Fourier's law of heat conduction, which is essentially the only law that you require, right, basically says that Qx is equal to minus Ka. So there's a little bit of confusion here that we are numbering the faces A and B and also using A for the area. But this is the area A, okay. So that it's a bad habit, shouldn't be done. I've sadly done it. So what it says is that the derivative of the temperature, right, across these faces, dt by dx. So this is the temperature derivative and this is the area. Okay, so you multiply the area with the temperature derivative. This is in a sense proportional to the heat coming in, right? And the constant of proportionality is negative. Okay, so basically what you are trying to say is that if there is a positive temperature gradient, so let us say that the temperature is increasing, then clearly the heat coming in has to be less than the heat that is kind of going out. And the reason is quite simple, that otherwise, how is the temperature increasing? The temperature is increasing because some heat is staying inside and then that is increasing the temperature of the volume. So that is why the negative sign comes. It's a matter of the convention, which way you draw the x-axis, which way you draw the y-axis. But the idea is clear, that is the temperature is increasing within the volume, which means that some heat is being captured, right? So what is coming out is less than what is coming in, hence the negative sign. And again, why is the area important? Well, the area is important because as I said, essentially you're looking at the heat flux, right? Heat per unit area. So that essentially tells you how much the temperature would increase, right? Because if the area is very, very large, then the temperature increase will not be that high. So that's all that we need to bear in mind, the Fourier's law of heat conduction, that's it. So what I can do is that this area over here, right, this area is essentially dy times dz, because again it's a small movement on the y-axis, small on the z-axis, so I can say dy dz. And then given the fact that I am looking at three different axes, this is nothing but the partial derivative on the x-axis, right? So this would be a more accurate way of looking at it because we have multiple derivatives. So what we would like to do over here is keep everything the same, the Fourier's law of heat conduction the same, but move to the partial derivative regime because we are only looking at the difference on the x-axis. So a little bit of algebra over here, not much I promise. So if I again look at the same volume over here, right, little region, this is dy and this is dz. So if I look at what's really happening on the x-axis, so what I can see is the heat that is entering minus the heat that is leaving divided by dx is nothing but the negative of the partial derivative. So this is easy. This follows basically from definition. It would have been positive if it would have been qx plus dx minus qx. That's not the case, hence negative. So this should be easy. So what we have actually done is that we have this result over here, right, which essentially tells you what is qx. So what we need to do is that we have qx minus qx plus dx here. We move minus dx over here and qx we had defined here. So we just stick this expression over there, which is minus k dy dz del t by del x. So the dot means multiply here. So what we have done is this part we have simply imported from the previous slide. So we come here. So basically the heat that remains within the volume, which is this thing, is nothing but, so these two are constants, so I can take them out, minus minus cancels, is k times dx dy dz, right? So the k is a constant of proportionality. We have not given it a name, but we will very soon give it a name. So then dx dy dz is nothing but the volume of the region. So let's call it dv for volume. So this becomes equal to the second derivative del square t by del x square, which is k dv del square t by del x square. Alright, so this is what it is, that the heat over here is equal to k times dv by del square t by del x square. So what I can then do is that I can do this across all axes, right, across the y-axis, z-axis and so on. So because of flow in all three axes, x, y and z, the total heat that remains within the volume is k times dv, of course. It is this quantity plus this del square t by del y square plus del square t by del z square, because it's a sum. So heat does not destructively interfere, right? Thermal energy, unlike electromagnetic energy, does not have any kind of destructive interference. It simply adds, right? So that's the second law of thermodynamics. So because of this addition, right, so what is happening is that we are adding them. So this is the total temperature derivative, and this amount of heat is remaining within the volume. So let's now introduce a new operator. The new operator will make our notation somewhat simpler. So let's look at this operator, del square by del x square, del square by del y square and plus del square by del z square. Let us name this operator nabla square. So you can see that this appears over here. So we will just refer to this as nabla square T. So the total heat that remains is the amount of thermal power. So note that the unit of this is not energy, the unit of this is watts. So the total power that remains, right, the total heat for a given unit of time, the energy that remains inside, right, so this is essentially energy by time, is nothing but k times dv, which is the small volume that we are considering, multiplied with nabla square T. Nabla square T is the temperature. So we will later on refer to this as a thermal conductivity, but we will do that when we will discuss the electrical analog of this problem, not now. So let's go with this and let us further assume that within this small volume it generates its own heat. For instance, if the small volume has a couple of circuits and those circuits dissipate dynamic power or they dissipate static power, then they are also not only transmitting but also generating. Let the rate of heat generation be Q dash joules, Q dash watts, right? It's power. So the total thermal power that enters plus that is generated within the volume dV, let us call it PST, like total, right, or everything, that is equal to K times nabla square T, which is the part that it kind of keeps, right, because your heat is flowing but some part it tends to keep, right. So that is why we have this temperature gradient plus whatever is internally generating, add both and multiply this with the derivative of the volume. So this Q dash is basically the derivative with respect to volume, right. So that's the reason we are multiplying it with dV. So this is the main equation that we use for heat flow or heat conduction, which essentially says that the power that is entering a volume plus that is generated is basically a sum of the second derivative of temperature computed in this nabla square way plus the heat, that is plus the internal heat generation, right. So essentially, given a small volume, what is the power that is being added to it is basically the second derivative of temperature multiplied with K plus Q dash. Let's look at another way of looking at PST. So then we will be able to kind of equate the LHS and RHS. So we'll compute this PST in a different way. So in this case, the earlier was a spatial derivative, right? So if you look at over here, there is no time yet. In a sense, this is just a spatial derivative. There is no time derivative. So we would like to also look at the time derivative thing and see whether we can kind of equate an LHS with an RHS. So PST, if you would look at our standard physics results way back when the concept of specific heat was defined. So we had said that the power that is kind of delivered to a volume is essentially its density multiplied with, of course, the volume with the specific heat, which is a constant for a given material, multiplied with the rate of temperature increase. So essentially what I do is, let's ignore the rest, but let's say the specific heat multiplied with the rate of temperature increase is basically the power inflow. In this case, of course, we are multiplying it with the small volume and the density. Now if I equate both the expressions for ST, this is a spatial derivative which is on this side, right? And then I have a time derivative which is on the other side, and of course the volume term gets cut. So this is equal to rho times Cp times del capital T by small t. This is one of the rare instances where actually we use a small letter as a variable, small letter t is time and capital letter T is temperature. In general, I also don't like doing that, but I have tried to stick with convention. In general, temperature is also represented using the variable U. But let me still go with the way that it is done. So we are kind of linking a second derivative of temperature in a spatial sense, spatial second derivative, with a temporal first order derivative, right? Time derivative with a spatial derivative. And then what I can do is, if I just divide this constant k, so it will be nabla square T plus Q dash by k is basically rho Cp by k. So k by rho Cp has a specific name. This is known as alpha. So essentially nabla square T plus Q dash by k is equal to 1 by alpha del capital T by del small t, temperature derivative. So a spatial derivative is equal to a temperature derivative is the key thing, key equation that we just derived. Now if we assume that there is no internal power generation, this term is 0. So then nabla square T is equal to is just proportional to del T by del T. And let's now do the other thing, which is that let us assume that the steady state, there is no increase in the temperature. then nabla square T is equal to the negative of the internal heat generation, which basically means that whatever is the spatial derivative, that is somehow being counteracted by the internal heat generation, leading to 0. So you can interpret this equation in many different ways, but the key idea is that we have a spatial derivative on one side and a time derivative on the other side. So this equation that we just derived is known as the Fourier equation of heat transfer. So this is the Fourier equation. So there are many ways of solving this. So a simple method is known as the finite difference method that is used. So it's not as accurate as the finite element method, but it's much faster. So the key idea is that we take a system of partial differential equations as we have here, and we converted it to a system of linear equations. So this is easy. We have all seen this. So let's say we take del square t by del x square. So all that we are doing is that for the same time instant, let's consider it for two different grid points. So what we do is that we take, if you're doing it for 2D, we take a two-dimensional geometry and divide it into grids. If you're doing it for, let's say, 3D, then we would divide it into small cubes or cuboids. In any case, let's assume that these individual grids, which are called elements, are numbered 1, 2, 3, 4, 5, 6. So essentially what we are doing is that we are subtracting this derivative at I plus 1 minus the derivative at I plus 1t minus it. So this is simple. This follows from the definition. This again follows from the definition that we replace a derivative with the values. So finally, this is what we arrive at. So this is roughly an approximation. Of course, for very small delta x, this is what this broadly corresponds to. So now let's look at the steady state solution of the Fourier equation. So this is nabla square T is equal to minus q dash by k. So as we have seen earlier, it can be converted to a set of linear equations if we consider all the three axes x, y, z. So finally, after doing all of it, a little bit of linear algebra is needed to appreciate this. But if let's say this is the power vector and this is the temperature vector. So what we do is that we take a chip and we discretize it into n cells. So let's say given a chip, we either have n 2D cells or n 3D cells. But in any case, we take it and we just, break it up, break. If you have n cells, so basically what we have T is basically a column vector of the temperatures at all n cells. A is an n cross n matrix which can primarily be derived by converting all the differential equation terms to matrix terms. So this is an n cross n matrix, and this was n cross 1. And power is again, the power vector at each cell, and the power is generating. So this is n cross 1. So we can easily see the matrix product makes sense. And all that we have to do is that for a given geometry, we'll have to compute this matrix A. Once we give it the power vector, which of course we can either get from a power simulation tool or we can directly measure with on-chip sensors, doesn't matter. In any case, once we have the power vector, all that we have to do is simply multiply it with this large n cross n matrix, and we will get the temperature vector. So of course, in this case, the complexity of the algorithm is order n square, right? So the reason is that we are taking, one row of n, one column of n, multiplying it to produce a single element and doing this n times. So as we shall see, this complexity is actually huge in the sense that this makes the algorithm quite slow and the algorithm becomes quite unresponsive, right? I mean, I'm sorry, it becomes quite slow, and because of this, faster approaches are often needed. So let us now look at the transient form of this equation. So the Fourier equation in its transient form looks something like this, which we have seen. So this is a linear transformation if we convert it to a matrix based linear algebra based system. So let's refer to the time derivative of the temperature T as T dash, and let's try to convert this equation into a linear algebra equation using similar finite difference approximations. So given that the second derivative is a linear transformation, we arrive at this point. If you would see, this is not very different from this in the sense that the other term is 0. We can simply say A inverse of the temperature is equal to power, right? So basically the term that is 0 is basically this derivative term. So in a sense they are related. So in this case we multiply the temperature vector, we'll see in 2 minutes why. So then the unit of this is power, the unit of this is power. Then the time derivative of temperature is again multiplied with another matrix which we shall refer to as the C matrix. So both G and C are n cross n element matrices which can very easily be found out by converting the differential equation that we have over here, a double differential on one side and a derivative on the other side. This can be done. So what we can do is that algebraically we can solve it for all time steps and then essentially kind of manually compute T dash, which is T at time k plus 1 minus Tk divided by delta small t. This is for time, this is for temperature. So this is done, this said and done, even the transient solution can be computed using a linear algebra based method. So there is again a fun part over here. So if you look at this equation again, we can convert it to an electrical analog, which basically means that the entire thermal problem can be converted to an equivalent electrical problem, and you can use a regular circuit simulator like SPICE to solve the electrical problem to actually get the analogous thermal values. We'll see in a second how. So let us map temperature with voltage. So let's just say that all temperatures here correspond to voltages in a circuit and power with current, right? So in this case, so this the temperature derivative is nothing but the voltage derivative in our converted world. So if you look at it, say this is V multiplied with, let's say, some constant is essentially is equal to I. So this constant over here is I by V, and by Ohm's law, I by V is basically nothing but the conductance, right? Is the opposite of resistance, it is the conductance. So G for that reason is called the conductance matrix, right? So for that, so even if you look at the term over here, the term K over here was called the conductivity, and as you can see, G over here, capital G, is the conductance matrix which is converting voltage to current. As you can see, this is happening. P of course is power, in our world it's current, in the electrical analog world. T dash is nothing but the temperature derivative over time, which is nothing but dV by dt. Any student of electrical engineering will immediately recognize that the capacitance times dV by dt is nothing but the current, right? So basically the current is equal to C times dV by dt. So basically again the unit of this is power, which in electrical analog is current. And C over here can be thought of as the capacitance matrix, right? It's the thermal capacitance, or it is the capacitance matrix, which is converting the time derivative of temperature to basically power, or the time derivative of voltage to current in the electrical analog problem. So what we have done is that we have taken a thermal circuit. This is the first time I'm using the word thermal circuit, mind you. So I'm taking a thermal circuit and I'm converting it into an equivalent electrical circuit. Why am I doing that? Because I can then use known electrical circuit solution methods, circuit simulation methods, to actually solve this problem. And in this case, I have an analog for voltage, which is temperature, I have an analog for current, which is power. And analog for conductance is this matrix G, and for capacitance is this matrix C. So if I look at an example, so as you can see, let's say this is a simple 2D or a 2D plate of silicon. So its electrical analog would look like this. So there's a thermal resistance between adjacent cells, as you can see, 1, 2, 3, 4, 4 thermal resistances. Furthermore, given the fact that this has a higher temperature, we are connecting it to ground with a capacitance. So the capacitance will indicate the fact that there is a voltage over here, and the voltage is nothing but a temperature. And of course, if any of these cells is also dissipating power, like in a static power or dynamic power, we can additionally add a current source. So basically, a complex thermal circuit is made using capacitances, resistances, capacitors, resistors, voltage sources. If let's say, it's a fixed voltage like the ambient means the outside, and current sources for power. And we always add a capacitor to ground to indicate that there is a certain voltage read temperature at a certain grid cell. Then once an analog has been made, there are a lot of algorithms for fast and ultra quick circuit simulation. Once we get the values, again we convert voltage back to temperature and current back to power. But anyway, we are simulating for temperature. So what ultimately matters is that voltages are converted to temperatures. So this was all about the finite difference method and its electrical analog. So this is, as you can see, it's nice and fast. But the finite element method is far more accurate, and most of the industrial tools use the finite element method, which is very accurate, yet somewhat slow, but still, in many cases, you need the accuracy. So what you do is that you convert the differential equation that we had, which is right over here, the differential equation, into an integral equation. Instead of derivatives, you kind of integrate both sides, so it becomes an integral equation. And we multiply the original integral equation, differential equation with test function v. So this is a standard, algebraic trick, a standard mathematical trick of multiplying multiplying both sides with a test function. But the test function, as we shall see, serves a very important purpose. Then what we do is similar to the finite difference method. We divide the domain. Domain is basically whatever geometry we are simulating. We can, in this case, divide it into many kinds. So we can divide it into triangles, rectangles, if it's 3D cuboids or tetrahedrons. So in general, dividing it into triangles for 2D and tetrahedrons for 3D is more common. The reason being that there are a lot of very efficient algorithms to kind of simulate temperature where the basic element is a triangle. Triangles are very interesting. If you would have followed the chapter on GPUs, the nice thing is that all the three vertices of a triangle are always on the same plane. And a triangle can be used to represent any kind of a complex surface. So each such basic structure is an element. And furthermore, the points at which different elements are connected, these points are the nodes. The connection points or the vertices of the triangle are nodes. Now what we do is, out of the integral equations with the test function, here again we create a set of algebraic equations. So this is always the case. Okay, this is common. But there are some important differences. I will explain them. Of course, this treatment is not meant to be self-complete. There are separate books on finite element methods. I would not like to get into that. But let fk be the value of the function fx, which is the function that I want to compute. For example, if I want to compute the value of the temperature distribution, then that would be, let's say, the function t. So I'm representing that generally as fx. So at each of the nodes, so recall that if I have a triangle, then the three vertices are the nodes. Given this triangle, let the value here be f1, the value here be f3, value here be f2. Furthermore, let me now bring in this test function, and let's say that it is some sort of a basis function, right? So what is a basis function? A basis function is, let's say, what sine and cos is in a Fourier series, or what your negative exponential is in a Laplace series. It's basically a set of those simple functions that can be linearly combined to produce a more complex function. So let's say at each of these points, let's say these be the basis functions at, let's say, v1, v2, v3. Now what we do is that we can express any function, let's say fx, right? So let's say this is point x, so I want to represent fx. It is basically f1 times the value of the function v1, where this is the basis corresponding to this node over here, f1 times v1x plus f2 times v2x plus f3 times v3x. So if you think about it, for every point within this region, I am representing it as a weighted sum of the basis functions, where the basis functions are different for different nodes, but they are evaluated at point x and weighted by the values of f1, f2, f3, etc. at these points. So this is how I can set up a bunch of equations, right? And of course, here the choice of the basis function is very important. And if I'm able to choose a good basis function, which is in a sense related to the final function field that I want to compute, then I can kind of represent the value of the final function, in this case temperature, at every point. And then of course it needs to satisfy boundary conditions and it needs to follow the physics. And I can set up a system of equations and solve it the same way I was solving it for the previous case. So I am not going more into the finite element method. I just have one slide. The reason is that, number one, it's very slow. It's not very apt for a computer architecture audience. They prefer the finite difference method much more. If I were to look at the finite difference method and electrical analog. So most of the popular temperature simulators in computer architecture, such as Hotspot, for instance, use the electrical analog of the problem and solve it. So of course, the commercial fluid dynamics tools, also known as computational fluid dynamics tools, CFD tools, they use the FEM method, but this is very, very slow, right? So in this case, the time is more than order n squared, much more. So given that they are slow, I can use another method known as Green's functions, which is ultra fast. So Green's function, the Green's function method is more like order n. And how does that happen? Well, we will use the concept of linearity and superposition. So if the total power profile is P is equal to Px plus Py, the final thermal profile we are assuming will be Tx plus Ty, in the sense, for this power I compute the temperature, for this power I compute the temperature, and I add them. And whatever is the result, the sum, that is equal to the thermal profile or the temperature profile. Then we have the notion of shift invariance, which means that for very large parts of the chip, other than, so let's say this is the 2D chip, and for very large parts other than the rim and the corner, right, other than this region, let's say anywhere in the center, let's say over here, the effect of a very small power source on its immediate neighborhood, be the power source here or let it be here, the effect on the immediate neighborhood is more or less the same. Other than the rim and corners, if you shift the power source, you shift the temperature profile. Think of it that way. So these two kind of immediately follow from the Fourier equation physics, but it is important to kind of note them or point them out separately, because much of the physics of Green's functions actually relies on this. So we have, as I said, linearity and superposition, which is this, and shift invariance. So what I am doing here is that I am slightly abusing notation. Previously, we had said that n is the total number of cells. Let me cut some slack for myself and say that now in this case it's an n cross n grid. Again, same symbol should mean the same thing, but my apologies. So in this case, if it's an n cross n grid, so at any point PQ, let us apply 1 watt of power. Then what will happen if this is a PQth point and I'm applying 1 watt of power? I will have a temperature profile which is radially symmetric. It's also called isotropic. What it means is the same in all directions. So it basically means it's same. All right. And this means that even gxy is equal to g minus xy. So using the properties of linearity and shift invariance, if I add the effect of all power sources, right? So what I can do is, if I want to find the temperature at point xp and yq, so what I do is that I look at all the power sources which are there at all the points. For each power source, let this be the temperature spread function, right? So this is what I did. This is the function via which temperature spreads. So what I can do is that given the power source xi and yj, given the fact that this relation is true, which follows from the fact that this function is symmetric, what I can do is I can say that, look, the effect of this power source at this point, which is my point of evaluation, is nothing but the distance between them, the x distance and the y distance. So g xp minus xi and yq minus yj. So this is simple common sense stuff. It's easy to prove as long as you kind of are able to visualize this. So what we are basically saying is that you consider all the power sources on the chip. For each power source, you add its effect, its temperature effect on the point of interest. What makes you think that we can add? Well, the first property makes us think that we can add, which is linearity and superposition. What makes you think that this effect is addable, and a power source here and a power source here will have the same effect here? Shift invariance. So what we do is we compute the distance. This is the temperature component that the power source here is adding at this point. And then we multiply this with the value of the power source. So this was of course normalized to 1 watt, but we multiply it with the value of the power source and then we just add up. So this is the final temperature. So as I said, this is another approximate method of computing the temperature based on the contribution of individual power sources and the temperature spread. So if I look at the continuous form of this equation, this would basically become a regular two-dimensional convolution, where this is the power multiplied with the temperature function of each source. So if this is a source and let's say its temperature is spreading like this, of course this is in 1D, but rotate it for a 2D effect, then pretty much all that we do is we find the power and multiply it with this. So let's say this is the source and you want at this point, this is the temperature. So now let me assume that the power source that I'm applying is very, very narrow, in the sense my cell size is very small. If that is what I assume, then the power source will become small, 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 and the magnitude of the power will still remain 1 watt. So this will approach the Dirac delta function, which basically is a function whose integral is 1. So this is 1 watt, its integral is 1. But pretty much it is 0 at all points other than at 0. So essentially it's a singularity at 0, where basically the value of the function, if I just plot it, right, the x-axis, y-axis, 0, 0, 0, 0, here there is a peak and again it falls down. So the integral over here is 1, but this is a very narrow function. This is of course theoretical, but I can define the Green's function as as follows. So of course there is a small error in this, so I would like to correct this. So what happens is that gradually when my power source becomes small, small, smaller and small, then I can assume that my power profile, right? So let's say this is a chip and I have a power profile, so I can kind of break it into small, 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 small grids. And each of these small grids I can assume to be a power source. And if this is small enough, I can approximate this as the Dirac delta function. So I can think that my power profile, right, is basically a collection of these Dirac delta functions, right? And all right. So what you see over here is that the moment I assume that my power source is a collection of these very small functions. So that is essentially also how we came from here to here. This was a simple summation. But then the moment you go from a summation to an integral, it basically means that your grid size is getting very, very small. So the moment we went from here to here, our power source over here started resembling this, which means that it became really, really small. It started resembling a Dirac delta function. The moment your power source becomes so small, so let me delete this part is not correct. The moment your power source becomes so small, the Green's function becomes the temperature profile of that ultra small power source. So this is the Green's function. So this equation over here can be replaced as T is equal to P convoluted with G. This is a 2D convolution. This is a convolution operator where P is the power profile, which is defined as what we just discussed. And the Green's function is defined as the temperature profile corresponding to a unit impulse power source. So this is known as a unit impulse. Why is it a unit impulse? Because its integral is 1, that's where unit comes from. And why impulse? Because it's a very narrow function, something that looks like this. So the moment I consider my power profile to be a collection of such impulses or Dirac deltas, then the temperature profile that this would lead to on the chip, say which let's say would be something like this, right? This would be the Green's function. So all that I need to do to compute the temperature is take the power profile and convolute it or convolve it with the Green's function. This is a very fast operation and this is linear in the number of cells, right? Previously it was quadratic in the number of cells, but this is linear in the number of cells. Hence it is much faster. So you see if you have 10,000 cells, it's 10,000 times faster, right? So a quadratic problem has been converted to a linear problem using this approach, which is quite important in this case. So now if you consider the Green's function, let's show what it means graphically. So graphically, as I said, we are treating each individual power source to be a single point, a point source, an impulse. See, that would look like this, right? It would be very well defined. It would look like this. But its temperature profile would show a spread. And as I have said, other than the rims and the corners, there will be a shift invariance also, which means that the function would look the same regardless of the power source. I mean, wherever the power source is, around it, this spread will happen. So this is what, let's say, a 2D spread would look like. You nicely see the density at the center and the spread towards the sides. So if we look at it, the convolution operation, so we incidentally use the same operation in neural networks as well. The reason there is speed, here also the reason is speed. It converts a conventional, operation, vector matrix operation into a purely matrix operation, right? So basically the previous one's complexity was order n square, but the current one's complexity is just order n. And the reason is, so in this case n means the same thing thankfully, so n is the number of grid points. And so previously, as I said, it was quadratic in the number of grid points, which was, if you think about it, a lot of work, a lot of extra work that we were doing, which was simply not required. In this case, it is just a function of the number of grid points. So a quadratic function has been converted to a linear function, or a quadratic complexity has been converted to a linear complexity, which makes the problem much faster. Now if I consider the leakage temperature feedback loop, so what I am seeing over here is that I have my dynamic plus short circuit power and the leakage power. They determine the total power, which again determines the temperature. The temperature again determines the leakage power, which again changes the total power. So there is a feedback loop over here. Most of the time it's a convergent series, but sometimes this can diverge. So what will happen is that the leakage will create so much of additional power that the temperature will then increase the leakage further. So this divergent condition will lead to a continuous increase in temperature until the chip shuts down. This is known as thermal runaway. So there is a fair amount of work in which I was involved to compute a leakage aware Green's function where we avoid this iterative feedback loop altogether, and the Green's function, the solution that it gives is actually the solution of the dynamic power plus the leakage power. So we have now discussed the power consumption model, the temperature model. So we are all set to look at methods for power and temperature management, in the sense we now know how power is dissipated, how the temperature increases. So we should now look at how do we manage the power and temperature effectively. This is a subject of the next lecture.